Our group will now present the lesson entitled Electric Current, Resistance, and Electromotive Force. Our first topic is about conventional current versus electron current. In the early 19th century, Benjamin Franklin, an American scientist, introduced the terms positive and negative charges. Then, electric current was defined as the flow of positive charges from the positive terminal to the negative terminal of the source of voltage. This current is referred to as conventional current. When electron was discovered, it became clear that the current in a metallic conductor is actually a flow of electrons from the negative terminal to the positive terminal. This is called electron current. Electron current is equivalent to the conventional current flowing in the opposite direction, as shown in the figure above. The conventional current was firmly established in scientific literature. Hence, most books still follow the conventional current.
Direct current versus alternating current. When the current that travels in one direction at all times is what you call the direct current or DC. While the current that changes directions at a regular interval, normally 60 times in 1 second, is what you call the alternating current or AC. When it comes to the flow of electrons, the electrons of the alternating current can keep switching directions. It can reverse its directions while flowing in a circuit, while the electrons of the direct current move steadily in one direction in a circuit. When it comes to the frequency, the frequency of the alternating current is 50 Hz or 60 Hz depending upon the current, while the frequency of the direct current is 0. In terms of the amount of energy that can be carried, alternating current is much safer to transfer over longer city distances and can provide more power than the voltage of the direct current because it cannot travel very far until it begins to lose its energy. Direct current or DC is supplied by cells or batteries and is commonly used in flashlights, calculators, automobiles, and cell phones. While alternating current is produced by AC generators distributed by electric companies like the Manila Electric Company or Meralco. That's why alternating current is most commonly used in the household appliances. Electrical resistance. Electrical resistance or simply resistance is the opposition of the material to the flow of the electric current. The SI unit of the resistance is ohm, which was named after the German physicist or mathematician George Simon Ohm. Electrical resistance is a force that counteracts the flow of the current. In this way, it serves as an indicator of how difficult it is to current to flow. Resistance causes some of the electrical energy to turn into heat, so some electrical energy is lost along the way. However, it is the resistance that allows us to use electricity for heat and light. In simple words, resistance is an important factor in an electronic circuit, which means higher resistance makes the current flow more difficult, and lower resistance makes the current flow less difficult. Most electrical connections make use of the devices called resistors to regulate the amount of current passing through a conductor. Some of the many types of resistors are shown below. Resistance values of the resistors may be fixed or variable. Potentiometers, light-dependent resistors, thermistors, and bar-wound rheostats have variable resistances, while metallized film resistors, carbon resistors wire, wound resistors, and chip resistors have fixed values. There are two sets of symbols that can be used to represent resistors. One is the International Electrotechnical Commission or IEC, and the other one is the American National Standard Institute or ANSI. There are different approaches to these standards. The American National Standard Institute or ANSI is prevailing standards body in the North America and select other regions, while the IEC or the International Electrotechnical Commission predominates in much of the rest of the world, and each takes a different approach to developing and approaching standards when applied to the different stages of electrical systems development. ANSI standards are design-based because the organization must adhere to strict North American legal and liability code, often tied to building safety, and they have more rigorous sets of rules to follow. While IC standards are applicable worldwide and across many countries where local practices, codes, and legal environments vary drastically, and the standards set in place are more performance-based than the ANSI. But in this discussion, ANSI symbols will be used.
Color code for resistor. So, the resistance of a resistor is indicated at its exterior or given in the form of color code. Previously, there were 4 colored bands in a resistor. The first 2 color represents the digit, the third color as the multiplier, and the fourth color as the tolerance. Now, there are 5 or even 6 band colors. The first 3 bands represents the first 3 digits of a resistance. The fourth as the power of 10 multiplier, the fifth band as the manufactured tolerance, and the sixth band as the temperature coefficients of resistance. For the next slide, color code for resistor, the figure below shows the 4, 5, and 6 band color code for a resistor. So, the 6 band resistor has a special property of temperature coefficient of resistance represented in ppm per Kelvin. So, the higher ppm value indicates that the resistor can withstand the higher or lower temperature. The ppm in the temperature coefficients of resistance means parts per million. This entails that the value must be multiplied to 10 to 6. So, the temperature coefficients of resistance will be discussed in the succeeding section. So, next slide. So, for this slide is the color code for resistor is, as you can see, there is black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, and silver. So, for the resistor acronym here you can see is for black is for B, B for brown also, R for red, orange for O, Y for yellow, G for green, B for blue, V for violet, V. So G as in for gray, W for white. So we can use resistor mnemonics like bad boys race are young girls, but violet generally wins. Or Betty Brown runs over your garden, but Violet Gray walks.
Electrical conductivity is a physical property of a material that determines the ease by which electric current flows through it when subjected to an electric field. Current density is the amount of the current per unit area of a conductor. It is represented by J. J is equals to I, which is the current, over A, which is the area. In some materials, the current density J is proportional to the applied electric field E, with a proportionality constant equal to the conductivity symbolized by the Greek letter sigma. That is, J is equals to sigma with electrical field. The SI unit of conductivity is Siemens per meter, symbolized by capital S over M. This combination of units is equivalent to 1 per ohm meter.
Factors affecting the resistance of a uniform wire. There are four factors affecting the resistance of a uniform wire. These are cross-sectional area, length, kind of material, and temperature. First, cross-sectional area. Resistance, or R, varies inversely from the cross-sectional area of the wire, which is represented by capital letter A. As the area increases, the resistance decreases. Thus, a thick wire has lesser resistance than a thin wire. A perfect analogy for this is the road. The wider the road, the less resistance it will offer to the flow of traffic along it. Recall that two quantities are inversely proportional to each other if their product is constant. Thus, if all other factors are not changed, the product of resistance and cross-sectional area must be constant. Equivalently, resistance sub 1 times cross-sectional area sub 1 is equal to resistance sub 2 times cross-sectional area sub 2. The second factor is the length. The resistance of a wire is directly proportional to its length. A longer wire has greater resistance than a shorter wire of the same material and cross-sectional area. Using the road analogy, the longer the road, the more the delay of traffic is experienced. Recall that if two quantities are directly proportional to each other, the ratio must be constant. Thus, if all other factors are unchanged, we'll have an equation: resistance sub 1 times length sub 1 is equal to constant, or resistance sub 1 times length sub 1 is equal to resistance sub 2 times length sub 2. The third factor is the material of the wire. The effect of the kind of material on the resistance of the wire is determined by its resistivity. Resistivity is the reciprocal of conductivity. Thus, its unit is omega times m, or ohms times meters. Conductors have small resistivities, while insulators have large resistivities. And semiconductors have intermediate values of resistivity. The table lists the values of resistivity for some materials. Note that resistivity is dependent on temperature. In the table, you can see different kinds of materials like aluminum, copper, gold, iron, etc. The effect of the length of cross-sectional area and material on resistance may be written as R is equal to resistivity times the length times the cross-sectional area.
For temperature, resistance and resistivity vary with temperature. As temperature increases, resistance and resistivity increase for conductors and decrease for insulators and semiconductors. In special alloys such as manganese and constantan, they hardly change with temperature. For superconductors, resistance and resistivity first decrease as temperature decreases, just like ordinary conductors. But at a certain critical temperature, resistance and resistivity drop to zero. The temperature dependence of resistance and resistivity is nearly linear if the change in temperature is not too great. An expression similar to linear thermal expression approximates the effect of temperature on resistance and resistivity. This linear relationship is given by Pt is equals to Po plus Pox times T minus To, and Rt is equals to Ro plus Rox times T minus To, where Pt is the resistivity of temperature, Po is the resistivity at reference temperature, usually 0 degrees Celsius or 20 degrees Celsius. Rt is the resistance at T, Ro is the resistance of To, and X is the temperature coefficient of resistance. The unit of X is reciprocal to that of the temperature, usually 1 over degrees Celsius.
Hi everyone! For the next topic, it is going to be ohmic and non-ohmic resistance. So resistance, it is also defined as the ratio of voltage to the resulting current. And in symbols, it is R is equal to constant is equal to V over I. So a resistor that has a constant resistance is said to obey Ohm's law and it is considered as ohmic. So otherwise, resistors are nonlinear or non-ohmic. For a non-ohmic resistor, the relationship between voltage and current may be complicated. So for example, for a light bulb, which is a non-ohmic resistor, the voltage versus current graph is a curve with increasing gradient. So this shows that resistance increases as current increases. Next is the electromotive factors and potential difference. So the flow of charges along a wire may be likened to the flow of water along a pipe. So for the water to flow along a pipe, a driving force supplied by a difference in water level or by a pump is needed. So similarly, to get the electric current flowing along a wire, a potential difference must be supplied. Some common sources of potential difference are electric batteries, solar cells, fuel cells, and even generators. So a battery, it consists of cells, and then each cell basically it consists of 2 electrodes and electrolytes, and then one electrode called cathode is connected to the positive terminal of the cell, while the other electrode called anode is connected to the negative terminal. An oxidation reaction takes place at the anode, releasing electrons in the process. So these electrons travel to the cathode where a corresponding reduction reaction takes place. The electrolyte provides the medium for transport of ions between the 2 electrodes. So yung standard symbol for a cell in an electric circuit is shown in the figure. So yung longer vertical line is the positive terminal, while yung shorter one is the negative terminal. So cells also offer small resistance to electric current. So this is called the internal resistance of a cell. Internal resistance, it is usually represented by the letter R. And then because of its internal resistance, the potential difference across the terminals of a cell when current is flowing through, it is less than when there is no current. So the potential difference across its terminals when no current is flowing is called electromotive force, or EMF for short. So electromotive force is the voltage indicated in a battery. So the potential difference across the terminals of a cell when current or letter I flows through it is called terminal voltage, and it is represented as capital letter V. So this is the working voltage of the battery, or the voltage for an external load. So the electromotive force and the terminal voltage are related as follows, which is V is equals to EMF, or yung electromotive force, minus IR.
For electrical power and energy, the power expended in an appliance is the rate at which it consumes electrical energy. Electrical power is obtained by multiplying the voltage by the current. In symbols, P equals VI. If the voltage V is in volts and the current I is in amperes, then the power P is in watts. Power may also be expressed in terms of resistance. Recall from Ohm's law that V equals IR. Substituting this in, P equals VI will yield the following alternative equation. The power rating of an appliance is usually marked in a label at the back or at the bottom of the appliance. The higher the wattage, the higher the rate at which the electrical energy is consumed. Whenever you pay your electric bills, you pay for the electrical energy consumption and not the power. Electrical energy consumption is determined by multiplying the power rating of an appliance by the length of time which the appliance is switched on. Electrical energy consumption equals PT. Its SI unit is joule. Note that 1 joule is equal to 1 watt per second. However, in electric bills, the energy consumption is given in kilowatt per hour. Next is the measurement of current, voltage, and resistance. The current, voltage, and resistance is an electric circuit are measured by an ammeter, voltmeter, and ohmmeter. Most of the time, these three measuring devices are combined to form a multimeter, which can be switched from one measuring device to another. An ammeter is a device used for measuring current. It is always connected in series with the circuit element to which the current is to be determined. An ammeter is connected by opening the circuit and then inserting it in line or in series with the circuit. An ammeter is a circle with the uppercase letter A. Voltmeter. A voltmeter is a device that measures the electromotive force or potential difference between 2 points in a circuit. A voltmeter is connected across or parallel to the part of the circuit element where potential difference is to be determined. A voltmeter is represented as a circle with an uppercase letter V.
Hi, I will tackle about house electricity safety devices. So many safety devices and features are considered in the design of an electrical system in the house or workplace. Household circuitry consists of several connected circuits parallel to the main power line. In turn, each circuit contains several parallel outlets. So because of this, appliances at home may be used independently of each other. However, using too many appliances at the same time may result in circuit overload. Electrical overloads happen when the amount of electricity passing through a circuit exceeds the capacity of a circuit. The wires may get heated and it may cause fires. To prevent overloading, fuses or circuit breakers are inserted in series or in circuits. So a fuse consists of a high resistance strip on an alloy that melts readily. For an instance, a 15 ampere fuse melts if the current exceeds 15 ampere. When the fuse wire melts, it blows up. A circuit breaker, on the other hand, is a large switch that is automatically opened by an electromagnet when the current is large. The fuse blows up and the circuit breaker trips when the current is excessive. This disrupts the entire circuit, thus preventing the current from flowing to the appliances connected to it. A blown-up fuse can never be used again, but a breaker that trips can be reset. So most electrical appliances use a 3-prong plug in their power cords, the two principal flat wires called live and neutral. These are the currents carrying wires, and the third prong or the round prong, it is a safety ground wire that carries no current. It is grounded to prevent electric shock in case a live wire accidentally touches a metal part of the appliances. So we all know that current not only affects the appliances but also the human body. The extent of injury depends on the amount of electric current that flows through the body, time of exposure, and path taken by the current. So here's the table of how the current affects the human body in the given time of 1 second. So 0 to 0.5, it has a non-effect to the human body. Next is 0.5 to 2.0, human will feel the threshold of feeling. Next is that 2 to 10 milliampere, human will feel pain and muscular contractions. Next is 10 to 15 milliampere, human will have difficulty or experience in difficulty in breathing. Next is 16 to 20 milliampere, muscular freeze or it cannot release or let go. Next is 20 to 100 milliampere, human body can experience respiratory paralysis. Next is that 100 milliampere to 3 ampere, human body will feel ventricular fibrillation. It will become fatal unless resuscitation is done immediately. And above 3 ampere can lead to death.
For our sample problems, sample problem number 1. An electrician experienced a mild shock when he accidentally touched a wire carrying 5 milliamperes for approximately 1 second. How many electrons constitute the given current? So ang given natin dito is milliamperes. Or pag kinonvert natin siya sa ampere, magiging 0.005 amperes. At ang time is 1 second. Ang formula na gagamitin natin dito ay Q is equal to IT, which is derived from the formula I is equal to Q over T. So ang I dito is current, Q is charge, and T is time. So proceeding to the solution, Q is equal to I multiplied by T is equal to 0.005 amperes multiplied by 1 second. Kakalabasan ay 0.005 coulombs. Dahil ang hinahanap sa problem ay number of electrons, proceeding to the formula or solution, 0.005 coulombs multiplied by 1 electron divided by 1.6 times 10 raised to negative 19. So, ang makukuha nating sagot ay 3.125 times 10 raised to negative 22 electrons. For our sample problem number 2. A copper wire is 2.5 meter long and has a diameter of 2.5 millimeters. How much current will it draw when connected to a 3 voltage source? So, ang given natin, which is, yung length is 2.5 meters. Tapos, ang diameter naman is 2.5 millimeters. At ang voltage is 3. So, ang formula, una muna is hahanapin natin yung area. A is equal to pi r squared. Tapos, hanapin natin yung resistance, which is yung R, is equal to P multiplied by length over area, or LA. Tapos, para makuha natin yung current, which is yung hinahanap sa problem, I is equal to V over R, which is derived from the formula R is equal to V over I. Proceeding to the solution, A is equal to pi r squared, may kita natin na ang given is diameter na 2.5 mm. At ang alam natin na yung radius is half of a diameter. So 2.5 mm divided by 2 is equal to 1.25 mm. I-square natin to at i-divide sa value ng pi, which is 3.14. Ang kakalabasan na area is 4.9 mm squared. Pero, ang kailangan dito sa solution is meters. So, i-convert natin ang 4.9 mm squared sa meters. 4.9 mm squared multiplied by 1 meter squared divided by 1,000 mm squared is equal to 0.0049 or 4.9 times 10 raised to negative 3 meters squared. So, proceeding to the formula ng resistance, ang P ay may uniform value na 1.72 times 10 raised to negative 8 meters. So, ang P, ibig sabihin nun, resistivity. At ang copper wire ay merong uniform na value nito. So, proceeding to the formula, R is equal to 1.72 times 10 raised to negative 8 meters multiplied by 2.5 meters divided by 4.9 times 10 raised to negative 3 meters squared. Kakalabasan ng sagot ay R is equal to 8.8 times 10 raised to negative 6 ohms. So, sunod na kukunin natin is yung current. So, I is equal to 3 volts divided by 8.8 times 10 raised to negative 6. So, ang makukuha nating sagot ay I is equal to 340,909.09 amperes. So, yun lang po. Thank you for watching and I hope may natutunan kayo.